Hello everyone, welcome to another episode on complete reference to CUDA programming. In previous episode, we have seen two parameters that can help us to improve the performance of CPU, that is clock frequency and pipelining. And we have seen both are having some limitations. Now let's explore the third parameter, that is transistors. So transistor is basic building block of logical gates on your processor. And idea here is that if you go on increasing more number of transistors on a processor die, then performance will be improved. So if you try to put more number of transistors on small area, then obviously it will increase the number. In short, if you try to make your transistor smaller and smaller size, then we can put more number of transistors in the same area. An advantage of the transistors is that if they are in smaller in size, then they require less energy to control the on and off, right? And it also requires less time to perform on and off. We'll not go into the details of how actually transistor works, what is that NP, N diode and collector, emitter, etc. It is not at all required, but simply we'll try to understand that what are the limitations of increasing number of transistors here. Okay, so currently the transistor size is 7 nanometer, though it is mentioned in this presentation it is 14. It is quite old, but nowadays it is common to have a 7 nanometer transistor. So most of the time if you see the specifications of these electronic devices, so we can see there is a line that is processor is of 7 nanometer technology or 14 nanometer technology. So that indicates typically the transistor size is of 7 nanometer. So if you see these size, or if you try to compare with DNA molecule, so 14 nanometer transistor is almost 14 times wider than DNA molecule. And to create one transistor, it takes 70 silicon atoms. And every silicon atom size is 0.2 nanometer. Now, if you see here, nowadays it is common to have 7 nanometer transistors. Maybe in future we can expect 5 nanometer, 4 nanometer and so on. Now if you go on increasing these number of transistors in the same area, now according to this Dennard scaling theorem, power needed to run transistors in a particular unit volume stays constant, right? So if you have a particular volume and if you put more number of transistors in that volume, then power needed to run this transistor remain constant according to the Dennard scaling. Now even the number of transistors are increased. However, if you go on decreasing the size beyond some limit, then this Dennard scaling may not hold, right? Because the reason is the leakage current was not considered in case of Dennard scaling. And if you go on reducing the size of that transistor, the problem of leakage current may arise. So question is how far we can go to reduce the size of the transistor. Right? So if you see the history here, it is depicted from 2000 onwards. So in 2000, size of one transistor was around 150 nanometer. Now we have observed across these 2 decades, the size of transistors is drastically reduced from 150 nanometer to almost nowadays 5 nanometer transistor is common, right? But what next? Can we, maybe in future I can say we are having a transistor which is of 5 nanometer, 4 nanometer, 3 nanometer, 2 nanometer, or maybe 1 nanometer. What's beyond that? We cannot have a transistor which is of less than 1 nanometer or less than one particular item. Okay, sorry for that. Okay, so that means if you see on this graph since 2000 onwards, initially the size of the transistor was around 150 nanometer. Then later on, the size is reduced drastically from 150 nanometer to around nowadays 5 nanometer. So size is reduced, but what is next? Maybe in future I can expect the size of transistor is around 3 nanometer, 2 nanometer, 1 nanometer and so on. But what's next? maybe I can have a transistor which is made up of only 3 silicon atoms. As I mentioned earlier, it takes nowadays 70 silicon atoms to design one transistor. Maybe in future I can have a transistor of only 3 silicon atoms. But what's next? Right? That means we are reaching already towards the physics limit. That means beyond that we cannot go and further reduce the size of your transistor. So this is the third option by which we wanted to increase the performance of your processor, but unfortunately this is also having some limitations. So we cannot go beyond that. Now other way is having another parameter, that is word length. So simply word length is nothing but number of bits processed by CPU in one go. As I mentioned earlier, processor fetches data from main memory, performs task, and again stores back the results into main memory. So word length is kind of a quantity that determines excuse me, number of bits can be processed by CPU in one go. So we already know that we have different types of processor like 8-bit processor, 16-bit, 32-bit or 64 bits. Nowadays it is very common to have 64-bit processor, but one decade back the 32-bit processors were there, but before that 8-bit and 16-bit processors were common. But how it affects the performance? When a processor needs data from main memory, it is done with word size quantities, and you can see here we have this diagram that depicts a processor that is going to fetch data from main memory, and the data main memory transfer the data on this data bus. So we have this address bus, database, and control lines are there. So simply address bus help us to find out the location from memory where we want to read the data. The data bus helps us to transfer the data from memory to processor, and the control line determines whether you want to transfer the read data or write data. That means you want to transfer the data towards memory or you want to transfer data from memory to the processor. To illustrate this word length concept, let's take a 64-bit processor we are having, and we want to perform addition of two numbers, and those are represented using 64 bits. Now if I take a 64-bit processor here, simply what I'll do, I'll first fetch those two numbers, then I can perform addition and store the results back. So which requires less number of cycles, because at the same time I can perform read the data that is of 64-bit, because the word length here is 64-bit. But if I'm having a 32-bit processor and I want to perform 64-bit addition on that processor, so in that case what I have to do, first of all I have to perform least significant 32-bit addition. Once that addition is completed, then I'll go and perform the most significant bit addition. So that means the operation is divided into two tasks now. So lower 32-bit addition followed by upper, or you can say upper 32-bit addition. So in this case, first lower 32-bit addition is performed, then we'll store that lower 32-bit addition in intermediate register, and it depends again, if carry is generated, then it will be forwarded towards the upper 32-bit addition. If not, we can directly perform the upper 32-bit addition here. Right? So that means you can see same addition of 64-bit numbers on 32-bit processor, which takes more cycles. So this way we can see that if I have higher bit processor, it is quicker to perform those operations. And now typically we have very common scenario that we are having 64-bit processor, and that is enough to perform our computations. So take this one example here. We have one processor. Here I'm having data bus, and this is main memory. And every you can say compartment here is having some address. So memory is divided into some compartments, and every compartment is going to have a unique address here. Now take one example here. If I'm having 200 megahertz DDR memory, that is the rate at which data can be transferred from this main memory, what is its theoretical bandwidth? So simply I'm having 200 megahertz DDR memory, D stands for dual data transfer rate here. So 200 multiplied by 2 here, and 8 bits here I am multiplying because we are having 8-bit data bus, and 10 to the power 6 emphasizing here is that we are having megahertz. That means with this configuration we'll be able to transfer 3200 bits per second. And if you want to convert into bytes, simply divide by 8, which will give us 400 megabytes per second. So that is the theoretical bandwidth. Now, if I change this 8-bit data bus to 16-bit data bus, it is very obvious that that data transfer rate is increased by 2. That is, now we'll be able to transfer 800 megabytes per second. Now, if we have this sort of configuration, that means higher the data transfer rate or higher the bandwidth, the more higher or the speed at which data will be fed to the processor will be high. So with this, processor will be able to perform computations at faster rate. Note that speed of processor is not increased here, rather than we are feeding the data at which processor can perform, or processor can perform the tasks. Fine. So this way also we can improve the performance. And 64 bits are now enough to feed the processor, which is of 4 gigahertz or 5 gigahertz clock frequency. Now, other way to think in case of this latency and bandwidth is, typically we want to reduce the latency. Latency means amount of time required to transfer data from main memory to the processor, and the bandwidth indicates the volume of data we can transfer from main memory to the processor and vice versa, right? So to increase the bandwidth, if you consider this water pipe here, so we are going to increase the diameter of this nozzle if you want to talk about increasing the bandwidth. And if you want to increase the latency, sorry, reduce the latency, we want to increase the force that is through which the water is traveling through this particular pipe. So typically, in order to increase the performance, we want to reduce the latency between memory and processor, and we want to increase the bandwidth. That means amount of data can be transferred from main memory to the processor. So these are the options by which we can explore. Now, just quick recap, some parameters that we have discussed, out of which are going to help us to increase the performance of the CPU. So we are having here 9 parameters. So take first one is a longer clock period. Question is whether longer clock period increase the performance of CPU or not. If you recall, I said faster clock frequency indicate faster CPU. But here we are talking about in terms of period or time. So time is inversely proportional to clock frequency. So if clock frequency is higher, that indicates smaller clock periods, and that, but here it is asked that longer clock periods. So longer clock periods indicates small frequency, and small frequency indicates slower CPU. So that's why first option is not suitable to increase the performance. By increasing the clock frequency, obviously we can increase the performance of the CPU. So second option is correct. More work per cycle, again somehow it is related to your pipelining. So if we can perform more work per cycle, definitely the faster will be the CPU. Fourth option is increasing the hard disk size. So obviously it has nothing to do with your processor speed, because processor speed can be determined by the clock frequency. So even though if you increase the hard disk size, it won't affect the speed at which CPU can perform the task. Same with the RAM. If you go on increasing the RAM size, maybe you will be able to put bigger size application in your RAM, but obviously it has again nothing to do with your processor speed. Increasing the transistor count, yes, we have seen that by increasing the transistor count, we can increase the performance. Then increasing the data bus width, will be able to feed at higher rate data to the CPU, but it won't increase the performance or speed of the CPU. Increasing the address bus width, definitely not, because address bus is simply used to find out the memory location in your RAM, so it has nothing to do with your processor speed. And finally, pipeline is another way to increase the performance of your CPU that we have seen in the previous episode. So that's it from this episode. Here we have seen two more parameters. One is data bus and other is transistor count. Now we have seen some parameters to improve the performance of your single core CPU, but of course there are some limitations and we are not able to go beyond that. Now in next episode we'll see what are the other ways to improve the performance of the CPU. Stay tuned for the next episode. Thank you all for watching.